My favorite things in the world are eating delicious food and drinking nice beverage. It's been a really good time. But as with all good parties in the end, we are left with a mess. And I'm not talking about spilled beer and food crimes. I'm talking about toxic levels of garbage in your body that need to be cleaned up before they kill you. Much of your chemical waste in the body needs to be sorted and disposed of. One system steps into back to clean up. This is your urinary system. And this lesson, we will talk about formation and excretion of urine. This is what we are going to focus on in this lesson. First of all, let's learn something about functional anatomy of kidneys and renal circulation. Each person contains two kidneys, so the functions of the kidney we are going to focus on contain regulating all sorts of important homeostatic stuff, like regulating your water volume, ions, salt concentration, and pH levels, and influencing your red blood cell production and blood pressure. How kidneys filter toxic leftovers from your blood, like nitrogenous waste made by metabolizing protein, and ferries it out of the body. This all involves the how, why, and what of your kidneys work. The kidneys are a pair of dark red face-lined bean-shaped organs that sit on each side of the spine. Let's take a cross-section of the kidney. So we slice a kidney, and this is what it looks like. Each kidney has three distinct layers. Beginning with the outermost is the cortex. Beneath that is the medulla, a set of cone-shaped masses of the tissue that secrete urine into tiny sac-like tubulars. And finally, the innermost layer is the renal pelvis that moves the urine out of the kidney into the ureter and into the bladder. When we take a magnified of the contents of renal pelvis, we found that each kidney is made up of 1 million filtrating units called nephrons. This is the structure of the nephron. The nephron is basic unit of structure of the kidney. Each nephron contains a round renal corpuscle that resides in the cortex, followed by a long and tiny renal tubulars that loops around between the cortex and the medulla. Structurally and functionally, nephrons are where the real business of blood processing. The urine making begins in 3 steps: glomerular filtrate, reabsorption, and secretion of renal tubular and collecting duct. First, the nephron could filtrate bulk transport of fluid from the blood to the kidney tubular. The process mainly depending on hydraulic pressure, and blood cells and proteins don't filter. Then the filtrated fluid was reabsorbed in tubulars, a process of returning filtrated material to the bloodstream. About 99% of water is filtered, and normally glucose is totally reabsorbed. Meanwhile, some toxins and foreign substances are secreted into lumen of the kidney from the blood, such as some drugs. So the bulk transport of fluid from blood to the kidney tubular is in glomerulus. The water and the solute resorbed and secreted in different segments of tubulars. Outside of the tubulars, there are capillaries surrounded. The nephron contains 2 sets of capillary networks. The first is glomerulus, and the second is vasa recta. Let's take a look at the physical anatomy of the kidney. Each kidney is made up of 1 million nephrons. They are made of renal corpuscles and tubulars. The outer part of the corpuscle is a cup-shaped feature called the glomerular capsule. Because inside it, there is a bed of capillaries called glomerulus. That's from the Latin word for ball of yarn, which is pretty much what it looks like. As we've seen, the renal artery divided and subdivided into very tiny blood vessels. They bring the blood into the nephron. What connects the corpuscle is the renal tubular. It actually has 3 major parts. The proximal tubular contains the proximal convoluted tubular and thick descending limb of Henry's loop. Thin segment of Henle contains then descending and ascending limbs. The distal tubular contains the distal convoluted tubular and thick ascending limb of Henry's loop. The upper part is the renal cortex. The below part is the renal medulla in the picture. First is the proximal convoluted tubular, or PCT, which is as convoluted as its name suggests. Then the tube drops into a dramatic hairpin turn called the nephron loop, or the loop of Henle, and finally it ends in distal convoluted tubular, or DCT, which empties into a collecting duct. All this twisting might make the tubular look like super insufficient, but it actually serves an important purpose, as you might expect. Just like with your small interstitium, the long curly shape of the nephron provides more time and space for it to resolve whatever useful stuff it can. And this winding path also allows the parts of the tubular that are towards the ends to have effect on process. There are two kinds of nephrons, cortical nephrons and just medullary nephrons. The glomeruli or cortex nephrons located in outer cortex. They have sources of Henle that penetrate only a short distance into the medulla. They occupied 80 to 90% of all nephrons. The entire tubular system is surrounded by an extended network of peritubular capillaries. They are involved in solute resorption. The just medullary nephrons occupied 10 to 15% of all nephrons. Their glomeruli lie deeply in renal cortex near the medulla and have long loops of Henle that deeply into medulla. Long afferent arterioles extend from the glomeruli down into vasa recta that extend downward to medulla, lying inside of the loops of Henle. They play an essential role in the formation of concentrated urine. This is the distribution of nephrons in the kidney. Cortex nephrons have loops of Henle that don't extend deeply into the medulla. The just medullary nephrons have loops that extend deep into the medulla. They all end into the collecting duct. We also have a section between the efferent and afferent arteriole called just medullary apparatus. The just glomerular apparatus consists of three parts. The macula densa is distal convoluted tubular epithelium modified. They could monitor salinity of the tubular fluids. The extraglomerular mesenterium is continuous with the intraglomerular mesenterium and is composed of cells that are similar in ultrastructure to the messenger cells. The just glomerular granular cells are located primarily in the walls of afferent, less commonly the efferent arteriole. They could secrete renin and innervated by sympathetic nerves. We are responsible for controlling our blood volume and blood pressure. There are at least three distinct inputs to the just glomerular cells: renal sympathetic nerves, intrarenal baroreceptors, and macula densa. They controlled by the flow of blood and filtrate fluid in the kidneys. Then let's take a look at the blood supply to the kidneys. The renal artery is the blood vessel that brings oxygen, nutrition, and waste products to the kidney. It divided and subdivided very tiny blood vessels. Finally, the blood vessels known as efferent arterioles. The efferent arterioles from the glomerulus is still oxygenated blood vessels. It brings the oxygen and nutrients to the segment of tubulars known as vasa recta. The renal vein receives the deoxygenated blood from renal vessel back to the systemic blood circulation, so the kidney contains two capillaries. the glomerulus and peritubular capillaries. The renal blood flow is with rich blood supply, about 20 to 25% cardiac output. High hydrostatic pressure in glomerular capillaries and low hydrostatic pressure in peritubular capillaries. The renal blood flow is relatively constant over an arterial pressure, a range of 18 to 118 mm mercury. But why? As we could see from the curve, the auto-regulation of renal blood flow and GFR is non-linear relationship. When the arterial pressure is range 18 to 118 mm mercury, renal blood flow is relatively constant. When the arterial pressure is beyond this range, the renal blood flow is increased with the arterial pressure, so that this could maintain the stable blood flow in the normal condition. Many factors affect the regulation of renal blood flow. The auto-regulation of renal blood flow is not explained yet. There are many theories. The first theory is genetic theory. Arterial perfusion pressure increases. More stretch stimulates to efferent arteries. Vascular smooth muscle contract more, resistance increases, and renal blood flow remains relatively constant. Another theory is tubular glomerular feedback. The flow of tubular fluid is secreted by macula denser and converted into signal that affects afferent arterial resistance and thus GFR alters. When GFR increases and causes the flow of tubular fluid at the macula denser to rise, the just glomerular apparatus sends a signal that causes vessel constriction to return blood flow and GFR to normal levels. In contrast, when GFR and tubular flow passes the macula denser decrease, the GGA sends a signal causing renal blood flow and GFR mainly by changing the resistance of efferent arteria. In addition, there are neutral and hormonal regulation. Essentially, all the blood vessels of the kidneys, including the afferent arteries, are richly innervated by sympathetic nerve fibers. Strong activation of renal sympathetic nerves can constrict the renal arteries and decrease renal blood flow and GFR. But moderate and mild sympathetic stimulation has little influence on renal blood flow and GFR. We saw constrictor agents such as NE and AVP decrease renal blood flow. We saw dilator agents such as NAP and nitrogen oxide increase renal blood flow. Then we will talk about glomerular filtration. Okay, this class is over. Thanks for your listening.